Hello, in today's session we'll be discussing semiconductor lasers. So this is an image of a semiconductor laser, and this is very familiar to all of us. And this semiconductor laser is an important laser because of its application in fiber optic communication. It has certain characteristics. It is size is very small and its cost is very low, and because of the direct conversion of electrical energy into light energy, it is very efficient. And because of these special features, semiconductor lasers are expected to find widespread applications. Here, the lasing medium is the semiconductors. So it is similar to a transistor and has the operations like LED, but the output beam has the characteristics of laser light. So the material which is often used in semiconductor laser is the gallium arsenide, and this is sometimes also known as gallium arsenide laser or injection laser or the junction laser or diode laser, etc. are the various names of semiconductor laser. And we all know that the basic principle of light emission from a semiconductor is the recombination of electrons and holes at a p-n junction when a current is passed through the diode. Here, three interaction processes are possible. One is the electron hole pair formation, that is, an electron in the valence band may absorb the incident radiation and get excited to the conduction band, and this leads to the generation of electron hole pair. And the second one is the spontaneous emission, that is, an electron may make a spontaneous transition during which it combines with the hole, that is, it makes a transition from the conduction band to the valence band, and this process it emits radiation. And the third one is the stimulated emission. Stimulated emission means the incident radiation stimulates an electron in the conduction band to make a transition to the valence band, and this process stimulated emission may occur. And in this animation will be explained all these three radiative transitions. And to demonstrate this process, we'll consider a band gap diagram of a semiconductor. So here EV is the valence band and this is the conduction band. EC is the energy of the conduction band. Here EC is the lowest energy level in the conduction band and EV is the highest energy in the valence band. So when a photon is incident, an electron in the valence band, it may absorb this incident radiation and get excited to the conduction band. Here an electron hole pair is formed. So here h nu is the energy of the photon and h is the Planck's constant and nu is the photon frequency. So when h nu is smaller than the band gap energy Eg, what happens? The electron will not absorb any energy and makes a transition. It will not make a transition. So they are not absorbed in the and the light is transmitted through the material. Here the semiconductor appears to be transparent. So the electron will remain in the valence band. So when the incident energy h nu is equal to the energy of the band gap, the electron in the this is the case when h nu is equal to the energy of the band gap. Here the electron in the valence band may absorb this energy, the incident photon, and it will go to the conduction band. Thus an electron hole pair is created. An electron hole pair is created. So this is the process of optical absorption. Now let us see what happens in the spontaneous emission. That is, spontaneous emission makes a transition from the conduction band to the valence band, and in this process it emits radiation. So this is an independent event that occurs when the electron give up energy as they make transition from the upper level to lower level. This photon emission occurs in random direction and it yields a spectral output with fairly wide bandwidth. So in lasers, we are interested in stimulated emission. That is, the incident radiation stimulates an electron in the conduction band to make a transition to the valence band. So let's see how it happens. If we have intense field of photons, these photons will stimulate the electrons in the conduction band. Each photon has energy equal to band gap. So this will stimulate an electron in the conduction band and it makes a transition to the valence band. Conduction band electron will be induced to drop into valence band and contributing a photon whose wave is in phase with the radiation field. So this is the process happening in the case of a semiconductor laser. Now the lasing requirements. In thermal equilibrium, since EC is greater than EV, the electron concentration EC will be less than the electron concentration in the valence band. So thus absorption is more likely to occur than the stimulated emission. To obtain the stimulated emission, the electron concentration in EC should be larger than in the valence band, that is the population inversion. So the number of electrons in the conduction band is greater than the number of electrons in the valence band. And another requirement is to enhance the stimulated emission over spontaneous emission. So for this we need a large photon density with the help of an optical resonant cavity. That is, one side is fully reflecting mirror and the other is the partially reflecting mirror. Here the photon density can build up to large value through internal reflection. So to initiate laser action we need a direct band semiconductor. Also we need stimulated emission, then absorption by population inversion, and also we need a large photon field density by having optical resonant cavity. So what are these laser structures? The first basic PN junction laser is called a homojunction laser. Here the same semiconductor material is used in both sides of the junction. You can see in this animation here the internal surface of the PN junction are polished to be mirrors. Two sides are roughened to prevent laser action across the diode cavity. One side is cleared to make highly reflecting surface. Thus, other side is also cleared, but it is a partially reflecting surface to make it as an optical resonator. And under appropriate biasing condition, laser will be emitted from this side. You can see in this picture. So now the energy band diagram of PN junction is shown over here. This is called a homojunction laser. That is, it has a one junction. In degenerate semiconductors, the Fermi level is below, and since we are at the thermal equilibrium, we get the same Fermi level on the inside, but it's above the conduction band edge. In both P and N regions, the area below the Fermi level is full of photons. So this is demonstrated in this animation. Holes are injected from P region to the depletion region. A recombination occurs and the currents flows in the diode. And if we are increasing the forward bias, high injection of electrons and holes into depletion region will occur. So here the electron in the conduction band is greater than the electrons in the valence band. Thus population inversion takes place. And another popular type of laser is the heterojunction laser. The previous one was the homojunction laser, and this is the heterojunction laser. It is the broad used heterojunction laser is the double heterostructure laser. Here a thin line of small bandgap semiconductor is sandwiched between two larger bandgap semiconductors. So this shows the working of the semiconductor. This is the block diagram of the semiconductor lasers. So if by some mechanism a large density of electrons be created at the bottom of the conduction band, and simultaneously a large density of holes will be created at the top of the valence band, and an optical beam with a frequency slightly greater than the band gap energy, it will cause a larger number of stimulated emission than absorption. And to maintain laser action, optical feedback should be provided. This is usually done by cleaving or polishing the ends of the PN junction diode at right angles to the plane of the junction. So when a current is passed through the PN junction under forward bias, so here it is P is connected to the positive terminal, so it is a forward biased. The injected electrons will increase the electron density in the conduction band, and the injected holes will increase the hole density in the valence band. And at some value of the current, the stimulated emission rate will exceed the absorption rate, and the amplification will begin. And if the current is further increased at some threshold value of the current, the amplification will exceed the losses in the cavity, and the laser will begin to emit coherent radiations. These are called injection lasers, since the laser action is created by charge carriers which are injected to the semiconductor. So we already discussed during the early stage of development, the semiconductor lasers were based on PN junctions and formed in the same material by proper doping, and that type of laser is called homojunction laser. But in the case of such lasers, the large current densities are necessary for the operation. So heterojunctions are introduced. Here, a junction formed between two dissimilar semiconductors. Nowadays, the semiconductor lasers are based on double heterogen junction, in which a thin active layer of semiconductor with a narrow band gap is sandwiched between two larger band gap semiconductors. So the advantages are its compactness, because it is smaller in size, simplicity and efficiency, and it requires very little auxiliary equipment for its operation. So the construction is very simple. No need of mirrors is needed in semiconductor lasers. It has high efficiency, and when a current flows, large number of excited electrons are produced in a junction diode. So only a small diode is needed to produce laser action. It is very efficient. It has the high efficiency, since nearly every electron injected across the junction contributes to a useful radiation output. And low power consumption is also its great advantages. It has certain disadvantages also. It is difficult to control the laser action due to extreme thinness and smaller size of the laser region. And also see, this semiconductor laser is dependent on temperature, so it affects greatly the output of the laser. And beam divergence is much greater of the range for 125 to 400 milliradians as compared to other lasers. And also the laser output is, that is, it is very wide beam. This is because laser action is between the edges of the two broad bands and not between two sharp and well-defined energy levels. So as a result, the monochromaticity of the semiconductor laser output is much poorer than that in other type of lasers. And also the cooling system requirement in some cases may be considered as its disadvantage. So this is all about semiconductor lasers.